Hello everybody, my name's Gus Lehrer. I'm pleased to be able to give my lecture, albeit remotely and albeit not in real time. I do apologize for not having made the long trek Sydney to Montreal. I would have loved to do so, but unfortunately on medical advice I've decided to stay home a little longer. I'm going to give altogether 3 lectures on the subject of invariant theory, classical, quantum, super. That's really not the whole story. What these lectures are really about is invariant theoretic approach to some of the really deep questions in algebra and geometry, which are outstanding today, and I hope that I can convey the connection and the efficacy of the methods that I'm going to use during these lectures. What I'm going to do, share my screen. I have prepared some slides. Right, so there we are. There's my title, and that's the first slide. So now let me begin by, I'm actually sitting in my home here, and when I look left, I see essentially what's in the image that I'm going to show you now. That, as you might gather, is the Sydney Harbour Bridge, and on the left is the Sydney Opera House. Further left again, you don't see it on the photo, but there is the metropolis of Sydney with its skyscrapers. On the right is the so-called North Shore. And if the image is being transmitted well, behind, a long way behind, are the Blue Mountains. It's that shadowy area that you can see. So this gives you some sort of a feel for the source of this broadcast. Without further ado, I think we'll get into the subject. So to begin with, what is an invariant? An invariant is some quantity which doesn't change when other parameters do change. So here is an ancient example of such a thing. If you have a quadratic form, a qxy, as I've written here, that can be transformed into another quadratic form by the substitution, linear substitution, which I've written down there. And then you get another quadratic form, which I've denoted by q prime. And then there are new coefficients, a prime, b prime, and c prime. And it is a fact well known to the ancients that if the determinant of the transforming substitution is plus or minus 1, then the discriminant doesn't change. That you can see very easily because the quadratic form can be written as q of x equals x transpose a x, where A is equal to the matrix A, B, B, C, the symmetric matrix. And that discriminant is nothing but the determinant of this matrix. And if you transform it by pre-multiplying by a matrix of determinant both plus 1 or minus 1, then obviously the determinant doesn't change. So this is an ancient example of an invariant. And discriminants were already recognized in mathematical literature, which is actually quite old, about around about the year 1000. People who were solving polynomial equations were already aware that discriminants were fundamental to the to the process of solution. Modern interpretation of invariant theory might be said to have been started by Gauss in his Disquisitiones right at the beginning of the 19th century, where he considered the classification of certain forms, although they were integral, and integral forms are going to form an important part of what we're talking about as well. So he was doing arithmetic, but it was still essentially invariant. To translate into a concrete problem, which really we're going to be looking at, and I want to look at sort of beginning steps in investigation of this during this first lecture. Suppose we have vector spaces, and suppose that they're modules for some algebraic object U, which has the property that you can take tensor products of modules. So this could be a group, more generally some sort of a Hopf algebra, even a bi-algebra, a Lie algebra. There are many contexts where such things happen. Then the basic problem that I want to address is to look at the structure of this iterated tensor power. Now, it might seem as though that is a rather special problem, but in fact, I hope to show you as we go along in these lectures, not today, of course, but this is actually many of the fundamental questions in algebra and some in geometry can be interpreted in this context. As I've stated it there, this is equivalent to determining the structure of the endomorphism algebra of this tensor power as a U module. There are two equivalent formulations, two more equivalent formulations, so three altogether, and I'm going to tell you each of them. The next one is a problem in linear algebra. You just take a tensor power of the dual space and then a tensor power of the space itself, and you look at the invariant elements under the operation of this G, which is the U that I've been speaking about. So the equivalence of these is not true in every case, but it's true in many cases. I'll be pointing it out as we go along. So this is a problem in linear algebra. So we've gone from associative algebra to linear algebra. And the next interpretation is an interpretation in commutative algebra. So we have, for some module, M for G, that's a module for its group ring over a field K, let's say. K of M denotes the coordinate ring. In this formulation, we are asking about the invariance in the coordinate ring, and that is a question in commutative algebra. And it's well known that that last question is equivalent to a problem in geometric invariant theory, namely the study of the orbit space of G on M. Now, the first interpretation, or first formulation, namely the decomposition of the tensor power, includes some very difficult classical problems, unsolved classical problems, such as what are the dimensions of the irreducible representations of these symmetric groups over a finite field. That is an unsolved problem, even for the field of two elements, where it has a lot of applications to things like cryptography and so on. There are classical analogues of these, where we take G to be some sort of an algebraic group over a field, often a reductive group over a field of positive characteristic is a very important case, where once again we have very, very incomplete knowledge of the situation. In general, the indecomposable summand of the tensor power are called tilting modules, and our objective is to understand their composition factors, and that is a key to understanding the representation theory of reductive groups, quantum groups at roots of unity, and so on. Now, applications are to a vast array of problems. As I've already mentioned, geometric invariant theory, or some aspects of geometric invariant theory are included. The first problem includes some very important classical problems. The rational G modules, where G is a reductive algebraic group. We're going to focus mainly on the first formulation, namely the decomposition of the tensor power. And my dog has demanded attention. It's all right, it's all right. So there are two aspects to this. If we want to understand the structure of the endomorphism algebra, then the two things we need to do is find generators for it and find all the relations among those generators. The former thing is called the first fundamental problem or theorem, and the latter is the second fundamental theorem. And what we're going to do is to first of all see how diagrammatic methods can be used to study these problems. In particular, we're going to have a close look at the Brauer category, but there are other similarly defined tangle categories, which I'll mention, which can be used to analyze this. Secondly, we're going to show how algebraic geometric arguments can be used to understand these fundamental theorems for classical groups and Lie algebras. And thirdly, having understood something about the endomorphism algebra in some case which is essentially tractable, for example, a semi-simple case, if we can detect the cellular structure in that algebra, then we are able to do some deformation, change the characteristic, and study the quantum case in a similar way. And finally, we're going to see how to apply these ideas in other contexts like quantum groups and Lie superalgebras and their quantizations. I want to start with the most basic case, which goes back all the way to 1901 in Schur's thesis, which is actually one of the great theses of history. So here we take V to be just a vector space, G to be the group of invertible linear transformations of V, an action of G on the tensor power, which is just given by a diagonal action. G acts on the individual tensor factors like this. In addition to that, the symmetric group also acts on the tensor power, and it acts by just permuting the tensor factors. And I've written it in this way to make it into a left action. So this is called an action by place permutations. And it's perfectly evident that these two actions commute with each other. So if you apply an element of the general linear group and then a permutation, that is, you get the same result as doing a permutation first and then applying the element of the general linear group. What that means is that we have a homomorphism from the group ring of the symmetric group to the endomorphism algebra that we are seeking to understand. And that is a start. In fact, as far as the first fundamental theorem is concerned, it's also the end, because as Schur proved, and this is the first fundamental theorem for GLV, this map omega R is surjective. In other words, the image of this map is the whole of the endomorphism algebra. I'm going to give you a sketch of this because although it's a very elementary and well-known fact, the proof is possibly not as well known as it should be. And it is indeed very, very simple. Depends heavily on semi-simplicity, as you'll see in a moment. And something like this is true in much greater generality than I stated it. And that is part of the message which I'm trying to convey. So to prove this, we want to prove that the image of omega is the full centralizer of the action of G on the tensor space. So let's write A for the image of the group ring of the symmetric group. That is a subalgebra of the endomorphism algebra of the tensor space, which is just a big matrix algebra. And let B be the subalgebra of E, which is generated by the operators in GLV acting on tensor space. Then we have these two facts. We've already observed that A centralizes the action of B and B centralizes the action of A. Now, A is a quotient of the group ring of the symmetric group, which is a well-known semi-simple algebra. It's a direct sum of simple algebras. And so by something which is generally given the grand name of double centralizer theory, but is actually very elementary representation theory, it is a fact that A is the full centralizer in E of B, if and only if B is the full centralizer of A in E. A equal to the centralizer of B is exactly what we're trying to prove. That is the first fundamental theorem. But to prove it, we're going to prove the latter. And the latter actually comes down to something which I characterize as polarization. It looks at symmetric elements. For example, A1 plus A2 is symmetric under the interchange of 1 and 2. But it can be realized in many different ways. So let W be any finite dimensional vector space over C. And again, I'm not stating this in anywhere near its full generality. And let's suppose that we have a spanning set at W naught, such that for any two elements of W naught, there are infinitely many lambda, scalars lambda, such that U plus lambda U prime is in W naught. Then the space of symmetric tensors is spanned by elements of the form with just U repeated, U tensor, U tensor, U, and so on. and that applies to, I mean, you can take an arbitrary element, U tensor W tensor Z, and symmetrize it. And what this polarization lemma tells you is that the result will be a linear combination of things like this. Now, let's observe that E, the endomorphism algebra of the tensor space, is actually the tensor space of the endomorphism algebra via this homomorphism. So a tensor product of endomorphisms acts just component-wise. And it follows that the centralizer in this big endomorphism algebra of A is just the tensor algebra in the endomorphisms of V, which are symmetric under the action of all permutations. So, for example, here is a symmetric element, A1 tensor A2 plus A2 tensor A1. That is symmetric under the action of the symmetric group on two symbols. But now we can apply the lemma with W being end V, and so this is what W is. Naught is GLV, and you can easily check the conditions. There's certainly GLV spans end of V. Every endomorphism is a limit of non-singular ones, and if you're given two non-singular ones, then there's an infinite number of these linear combinations which are also non-singular, because the condition of being singular is a polynomial condition on lambda. So only a finite number of lambda will be excluded. So certainly a polarization lemma applies, and the conclusion is that the centralizer of A is spanned by these elements G tensor G, and so on. Now, unfortunately, yes, that's all right. And that is exactly the second thing, the second statement, which I have now proved, and therefore the first statement is also true. Now, what about the second fundamental theorem? That is, all the relations among the elements G tensor G, etc. Well, we have the finite number of generators, namely the permutations, and to describe the relations among them, what we are really asking is for a description of the kernel of omega R, of this map from the grouping of the symmetric group into there. We want to understand the kernel. Well, to start with, we have one element in the kernel which is very obvious. If we write ER minus for this alternating idempotent in the group ring of the symmetric group, then if we take the particular case when R equals M plus 1, remember that the dimension of V is M. And if we apply this element of the group ring to the tensor space, then we get, of course, alternating tensors. In other words, if you take any element of the symmetric group, then operating on anything in here by it just gives the sign of the permutation times what you started with. But there are no alternating tensors of degree M plus 1 because the dimension of V is just M. And you remember that the exterior power, or the alternating power, has a basis of elements of the form VI1 wedge VI2 and so on, wedge VI M plus 1. where these are basis elements. The VI are basis elements of V. But the thing is, if you have m plus 1 here, then you have to get at least one repetition, and so this thing is equal to 0. So here, that's one element of the kernel. So in particular, if R is at least m plus 1, then the kernel contains that element E m plus 1 minus. And in fact, Chaire showed that that element, that single element, generates the whole of the kernel. Of course, you need R at least equal to m plus 1 to have that element in the group ring. But if R is smaller than that, then you have an isomorph. So the proof of this result is a little more difficult than the proof of the first fundamental theorem, because you need to know something about the representation theory of the symmetric group. So the first thing you need to know is that its irreducible representations are parameterized by partitions or Young diagrams, if you like. So here is an example of a Young diagram. This corresponds to a partition 4, 3, 2, 2. So that's a partition of 11. So lambda runs over all of these partitions. Now, the kernel of the omega R has to be a sum of certain of these two-sided minimal ideals, because every ideal is. And so we need to determine which lambda are in the kernel. And so let IK be the set of partitions, or the sum of I lambda over those partitions where lambda has at least k parts. So if you have this partition, then this here is greater than or equal to k. The proof consists in showing this chain of inequalities. So E m plus 1 minus generates this ideal. That's contained in n. We've already seen that. The next inequality, n contained in here, is in some sense the most difficult thing to prove, and it's not all that difficult. One shows explicitly that if m doesn't have m plus 1 rows, then omega r of the corresponding ideal is not equal to 0. So you need to know how the representation corresponding to lambda is constructed. So, and that uses some of Frobenius's theory. Frobenius, of course, was Chaire's mentor and supervisor. So that's how the second inequality is proven. And the last inequality is a standard fact about induced representations. Again, something which Frobenius invented. And so once one has that, then of course this chain of inequalities do show that n is generated by this single. Equivalent formulations of the first fundamental theorem, as I mentioned. So let's start with linear algebra 1. If we take some tensor power like that of the dual space and then the space itself, and then look at the invariants of GLN in there, then you have 0 if R is not equal to S, and you know what a generating set is by translating what we already know about the endomorphisms. And it turns out that these are the generators, the linear generators. You just take this tensor to this product. it's a multilinear product, of course. The third formulation says that if you take this space, then the set of all invariant functions on this space, invariant polynomial functions, are generated as a commutative algebra by the quadratic functions taking this tuple to just phi I of vj. That is a function of degree 2 in these variables. Now, you can state the second fundamental theorem in those other contexts as well, but it is actually quite complicated to formulate, and it's much more efficiently done in using the language of diagrams, which we don't yet have, but we will shortly have it, and I will come back to that in a subsequent lecture. Now, let's move on from the general linear group to the classical groups. Let's suppose that our space has a non-degenerate bilinear form, and take G to be the isometry group of this form. So that's what G is. And we assume furthermore that the form is either symmetric or skew, and therefore its matrix can be, if it's symmetric, can be taken to be the identity matrix, and if it's skew, it's the space is a sum of so-called hyperbolic planes, and so the matrix of the form can be written as I've written there, JM. So it's just a whole lot of these matrices concatenated with each other. In the symplectic case, you need an even dimensional space for it to be non-degenerate. Now we want to find a first fundamental theorem and second fundamental theorem in this case. In other words, we want to analyze the endomorphisms of tensor space which commute with G. Well, since G is a subgroup of GLV, you still have those endomorphisms which arose when we were looking at the GLV case. Namely, I've changed notation here to eta because eta is the same as omega. That means you just act by place permutations. But in the symplectic case, it's actually more convenient to have a sign in here, namely this epsilon pi, and epsilon is the sign of the permutation pi. You have those endomorphisms that you had before, namely the place permutations. But in fact, you'd expect more, and indeed you have more. So here is an example of one extra invariant. If we take take a basis of V, take a dual basis, so that's the case, then we can form this element C0, which is a Casimir-like element, and so it's actually independent of the basis, and it's invariant under the isometry group. That is easily checked. In fact, the easiest way to check it is that it corresponds to the identity element under the isomorphism that end V is isomorphic to V tensor V in this case. And then we have this endomorphism of the tensor square, namely that V tensor W goes to the inner product of V and W times this invariant element. When we apply E to that element, you get this. It's furthermore the case that E squared is equal to epsilon, where epsilon is plus or minus 1, times the dimension of V times E. So it's almost an idempotent. Now, we can manipulate a little bit here to make the observation that in the linear interpretation, that this space here, which is the one that we're interested in when R equals S, is isomorphic to this space, which is just a linear space. And furthermore, because minus the identity always is in both the orthogonal group and the symplectic group, because it acts as -1 to the R, the parity of R and S have to be the same in order for this to be non-zero. So now let's explore some relations among these elements of the endomorphism algebra, which we already have. So we have E, this endomorphism of V squared, and the permutations. In the symplectic case, it's permutation times the sign, possibly. So we define EI to be this endomorphism algebra, this endomorphism, where this is in space, it acts on the factors I plus 1. And SI is just this. SI squared is 1. And we've just seen that EI squared is epsilon m times EI. And we know that the SI, because they do so in the symmetric group, satisfy the braid relations. And we also have this. We'll see more of these later, so I won't explain why, but it is actually true that this is the case. I'll ask you just to believe that for the moment. There are some further relations which are a bit less obvious. You can verify all of these by simple calculations. You can, they're all straightforward. There's nothing tricky about them. And it is the case that we have the first fundamental theorem for the classical groups that the endomorphism algebra is generated by the permutations and these extra endomorphisms EI. By the way, you only really need E1 because you can transform E1 into any of the other EI just by simple manipulations. This was first proved, I think, by Hermann Weyl, although it's a little bit shrouded in antiquity. It is certainly proved in some sense in Hermann Weyl's book on the classical groups, using some tricks, including Capelli identities and so on. And one of the things I'm going to show you is how this theorem can be proved, and others which are sort of deeper and more complex can be proved using some methods in algebraic geometry. And an equivalent formulation, in fact, it's a good exercise. In fact, I'll write down here that this is an exercise to show that this statement is equivalent to the theorem I've just stated. That if you take an even, remember this has to be even because remember hom t to the r t to the s is 0 unless r and s have the same parity, and then when you add them together that means you get an even number. So here are some natural invariants. These linear functionals are obviously invariant because the form is invariant under the action of G, and therefore these linear functionals are invariant, and in fact, there's nothing else. And now, these statements, although I confess we haven't proven them yet, but these well defined statements can be interpreted in terms of diagrams. And that's what I want to show you briefly now before finishing the first lecture. The Brauer diagrams and the Brauer category are defined as follows. We're given a ring and an element of this ring, and that's all. Then the Brauer category, B, R delta, where I guess the R should be, these two R's should be the same, is defined as follows. Its objects are the natural numbers, and morphisms are diagrams from R to S, or linear combinations of diagrams, I should say, are linear combinations of diagrams. And a diagram from R to S is a picture I'm going to show you now. It's a diagram from 6 to 4. As you can see, there are 6 dots on the bottom and 4 dots at the top, and you can join them in pairs in any way that suits you, and that is a diagram. Every morphism is a linear combination of those. Now, composition of morphisms is by concatenation of diagrams, as you can imagine. But when you concatenate diagrams, for example, you might get something like this. You concatenate those, you get what we say is that this is replaced by delta. There's a more formal way of putting that, but you just take away all these free loops. They can arise in a more complicated way than this, but you just, and they can be nested. You can get them like this. And so there are more subtle variations on this definition, but which reflect the topology better. But really all that counts is the number of loops at this stage. So we have a category because we can compose morphisms. It's a tensor category because if you take 2 integers, their tensor product is just their sum. That's on objects. And on morphisms, you just take 2 diagrams and juxtapose them. It's a theorem which is actually proved in a paper of myself with Juin in GEMS. I'll give you references at the end of the last lecture. That this is generated as a tensor category by the 4 morphisms I, X, A, and U, those 4 which I've drawn there. So it's X is, for example, a morphism from 2 to 2, A is a morphism from 2 to 0, and U is a morphism from 0 to 2. There are 7 relations, and all relations follow from them. And so I'll just give you a feel for what they look like by showing you the relations depicted as diagrams. Well, that's a double crossing. That just says that X squared is the identity tensor of the identity. The braid relation just says that you can move this across. That's what the braid relation is. It's more commonly stated with overcrossings and undercrossings, but and of course that arises too, but it is one of the relations. D-looping is simply that. There's no cost to D-looping. There are other categories where D-looping comes at a cost. Loop removal, well, I've just been through that. It's where you replace a closed loop by delta. The sliding relation is very natural. You can slide this across to the other side. And finally, there is the straightening relation, which is this. It looks very natural. So all of these relations are quite natural, and it can be shown that they suffice to define the Brauer category. Now, before I finish today, I just want to show you that from these very humble and simple beginnings, the Brauer category can be you can express some rather complex phenomena in terms of this very apparently simple category. So we have this isomorphism from R to S. So suppose you have a diagram from R to S, then what you do is you put that there and then put that there. So you pull a strand down and you get a diagram from R plus 1 to S minus 1. That's so that I've just written in in algebraic way, and the inverse is when you do the opposite, where you take something and pull it up. And of course, when you do one and then the other, you get back to where you started from. Now, we can do calculus in the Brauer category. We're going to see that in a moment, but let me just point out this important fact. I'll point it out again later, but the Brauer algebras are generally non-semisimple, because you see here in particular, it says that if once Z is greater than or equal to R minus 1, then all of these are not semisimple. That fact was proved using cellular theory by Rui and C. And I want to just finish by pointing out some special morphisms. So we've got this X where, and so you have the permutations, which can be realized like that. It shouldn't have any triple crossings. So the symmetric group is actually a subgroup of this algebra, and its group algebra is a subalgebra. And there's an important special morphism, which I write as sigma epsilon of R. It's defined there. It's alternating in the case of the orthogonal group and symmetric in the case of the symplectic group. So we just denote it by that diagram. And there are various facts. So, for example, you have this fact here. So this just says exactly what I said in words, that when epsilon is plus 1, this is alternating, and when epsilon is minus 1, it's invariant. It's invariant under the symmetric group. That little calculation which I've shown there is that in the symmetric case, then in the orthogonal case rather, you have this sort of relation. Whenever you have a loop, then you get 0. And this is a property called harmonicity, harmonic diagram. So in the orthogonal case, this special morphism is harmonic. Now, I don't expect you to remember this or even think what it means, But here is an example of the degree of complexity that you can come to when you play games with these diagrams in the Brauer category. This is an equation in the Brauer category, and as you can see, it is quite non-trivial. I see, it was incomplete. And with that, the end of the first lecture. Thank you very much for your attention.